Welcome back, Focus Learners, to today's Explainer. Let's jump right in because we are tackling an absolutely massive paradigm shift happening right now in enterprise AI architecture. Listen, if you've been relying on standard prompt engineering or just tweaking system instructions to secure your autonomous agents, you are basically building a house on sand. The hard reality is, soft constraints like prompting are failing us. They're non-deterministic, they're super easily bypassed by bad actors, and frankly, they eat up way too much processing budget. So today, we're exploring the definitive fix for this, the major shift toward hard architectural control planes using hooks.
Here is our architectural blueprint for the day. First, we'll unpack the dual-layer control plane. Then, we'll look at symbolic hooks and runtime interception. From there, we'll zoom out to multi-agent orchestration, before diving deep into sub-symbolic neural steering, and finally, we'll wrap up with auditing activation trajectories. Let's get to it.
Section 1. The dual-layer control plane, shifting from soft constraints to hard execution limits.
Okay, let's dive into this. So traditional safety methods, things like RLHF and standard prompting, those are what we call soft constraints. They're probabilistic, which means they're highly susceptible to adversarial jailbreaking. They're more like suggestions than actual rules. Enter the bifurcated control plane. This is a decoupled architecture that uses hooks to strictly separate your operational logic from your security boundaries. In this setup, the AI model still decides what it wants to do probabilistically, but a completely separate deterministic hook script decides if that action is actually allowed to run. It's a hard limit, no exceptions.
Now, you might be wondering, what's the real difference between traditional rules and these architectural hooks? Well, rules are static. They're general guidelines that get applied globally across the whole system. Hooks, on the other hand, are dynamic and totally context-aware. They essentially sit there waiting and are triggered by specific system lifecycle events to execute custom scripts that alter active sessions in real time. This dual-layer approach is a total game-changer. It provides the exact defense in depth you need to satisfy those incredibly strict governance requirements, like the EU AI Act. Because honestly, if a model misbehaves, that hook layer stands as the final unbreakable structural barrier.
Moving on to Section 2, Symbolic Hooks and Runtime Interception, Governing the Execution Loop.
Zooming in on the symbolic layer for a second, it's fascinating to look at how different enterprise frameworks actually handle runtime interception right on the developer's machine. Azure SRE, for instance, configures hooks via a REST endpoint or some structured YAML, relying on independent evaluator models for prompt hooks and sandbox scripts for command hooks. But on the flip side, tools like Claude's Code and Cursor take a highly system-native approach. They rely heavily on standard output and process exit codes. For example, Claude literally uses process exit code 2 as an immediate, hard-blocking signal. It completely cancels the action and feeds the error right back into the model's loop.
Now, what's really interesting here is how this looks in practice. This is an exact JSON payload from Cursor, showing a hard execution block. The system parses the standard output, sees the permission is explicitly set to deny, and boom, it halts the system file modification instantly. The model gets that agent message error fed back to it, while the human user sees the clearer user message. It's clean, fast, and secure.
Frameworks like Claude use a very strict priority chain for these evaluations. It goes like this: deny overrides everything else. Defer overrides ask. Ask overrides allow. The whole system is secure by default. And here's a massive bonus you might not have thought about. Returning these structured outputs from a hook means frameworks can sometimes skip model inference steps entirely. Seriously, if a hook just pulls a cached result and returns it directly, you totally bypass the model call. That saves you significant latency and a ton of API costs.
All right, Section 3, Advanced Multi-Agent Orchestration, State Tracking, Trust, and Memory.
As these AI systems scale up into really complex multi-agent architectures, hooks literally become the absolute backbone for maintaining system reliability across dozens of moving parts. System architects are using them to deploy some pretty advanced orchestration patterns. For example, when dealing with flaky networks, hooks assign unique deduplication keys, maybe combining an agent ID with a hash of its arguments, and store them in Redis. This ensures idempotent actions, which means absolutely no duplicate network executions. Hooks also manage resilient fallback chains using strict timeouts to route failures to alternative agents. They can even trigger sensory feedback, like audio chimes, so developers know what's happening without staring at logs. Plus, they decouple memory. They push all that heavy context bloat completely offline into graph databases like Neo4j, which keeps your active context window lightning fast.
And in these multi-agent setups, static access is out. Instead, agents dynamically track each other's reliability. Think of this little math formula as a narrative of trust. When an agent succeeds at a task, it earns a modest plus 0.10 to its score, but if it fails, it is penalized significantly more heavily with a minus 0.15. This asymmetric scoring is absolutely crucial because it protects the broader system, ensuring that only the most highly reliable agents are ever allowed to delegate critical tasks.
Let's move to Section 4, Sub-Symbolic Hooks and Neural Steering, diving into the mechanistic inner core.
Okay, we are leaving the runtime environment entirely now and shifting straight into the matrix. Using PyTorch forward hooks, we can actually intercept and directly alter the model's internal residual stream during inference. Now, you're probably thinking, doesn't intervening inside the neural network completely tank performance? Actually, no. The computational cost is astonishingly minimal. Applying these steering vectors takes less than 0.1 milliseconds of processing time and uses just 4 kilobytes of memory per layer. It is incredibly, surprisingly efficient.
So how exactly do we pull this off? It's done through something called representation engineering. Let's make this dense, high-dimensional math a bit more accessible. It's essentially 3 steps. Step 1, we collect pairs of contrast of prompts, say an example of secure code versus an example of insecure code. Step 2, we run both sets through the model and capture the hidden state activations at a specific targeted layer. Step 3, we simply subtract the mean of the negative activations from the mean of the positive ones. The resulting difference? That gives us a precise steering vector that isolates that exact concept deep inside the model's brain.
And this brilliantly illustrates what happens next. When we apply that vector back into the model during inference, we scale it by a steering coefficient, which we call alpha. And let me tell you, the transformer is highly sensitive to this number. At a subtle 0.5, you're just getting minor style tweaks. Push it to a moderate 2 to 4, and the target behavior is strongly emphasized while keeping good grammar. But push it aggressively past 8, and the model's coherence starts dropping fast. And if you oversteer it past 15, you literally push the vector completely outside normal hidden space bounds, resulting in total, incoherent generation failure. To make this internal steering even more precise, engineers use sparse autoencoders, or SAEs. Here's the deal. Raw neural activations are polysemantic. That means a single neuron might fire from multiple totally noisy, unrelated concepts at once. It's a mess. SAEs resolve this superposition. They reconstruct those tangled hidden states into clean, distinct, monosemantic directions. This is a huge breakthrough because it allows us to cleanly trace exactly how specific internal features influence the model's final token predictions.
Which brings us to our final section, Section 5, Auditing Activation Trajectories, Real-Time Telemetry, and Defense. Taking everything we just learned about the internal matrix of the transformer, security engineers are now using this for real-time defense. They don't just wait for the output text to generate anymore, they monitor the internal vectors while the model computes, literally token by token. They rapidly track 5 key representational drift metrics. We have drift magnitude, representing the vector change between tokens, cosine similarity, tracking directional stability, cumulative drift, which measures the total path length traversed, drift acceleration to catch sudden trajectory changes, and mean drift to establish a healthy running baseline.
And here is the absolutely crucial takeaway. By tracking all that, we can identify a specific telemetry signature. When an adversarial attack or a clever jailbreak hits the model, its internal trajectory deviates wildly from its baseline. This signature is unmistakable. You'll see a sudden spike in drift acceleration combined with an immediate drop in cosine similarity. By monitoring this telemetry in real time, safety controllers can instantly halt token emission the exact millisecond a representational anomaly is detected, long before the bad output ever reaches the user.
Which brings us to the ultimate provocative question for anyone building autonomous systems today. Are your AI safety measures just soft suggestions hidden somewhere in a prompt, or are they hard, architectural hooks? This shift from probabilistic guidelines to deterministic execution limits, it isn't just a nice-to-have upgrade. It is a fundamental requirement for the future of reliable, enterprise-grade AI. I really hope this explainer gave you the blueprint you need to rethink and reinforce your own agent architectures. Keep learning, keep building, and I will see you in the next one.